organizers as well for giving the opportunity to speak here. I'm going to talk mostly about these two works, and one is the details are not out yet because it's in the proofs. So what I do with our group in Singapore, we work a lot on many-body open quantum systems, and we look at issues related to out of equilibrium phase transitions, how to use dissipation to probe a system, and how dissipation can be used to generate interesting correlations, and various relaxation regimes, exponentials, power law, and so on. And once you deal with open systems, and then we try to figure out things regarding energy conversions, so quantum thermodynamics as well, and problems of transport, which I will discuss today. And of course, stabilities. Suppose you have a many-body systems and you connect it to an environment and you want to see how stable it is against dissipation. And often we use a matrix process algorithm to try to handle systems which are relatively large. More recently, we also applied a matrix process algorithm to machine learning. And I'm not going to talk about this now here, but if you are interested, it's actually quite a nice direction of the connection between many-body quantum physics and machine learning that I'm happy to talk about. Anyway, today I would like to talk to you about these two works. First of all, about spin ratification, which I did with some of the collaborators, which are also here, Beninti and Casati. And then another one on many-body localization and dissipation, which we did with one future PhD student, he hasn't started his PhD yet, and one past PhD student just finished. So let me start with the spin ratification. A diode has a characteristic curve given here. I just show a typical characteristic curve, IV curve. You have a current that increases significantly when the bias, the voltage is positive, and then it's very small when it's negative. So we can think of now our rectifier is a quantum system, and I put two buffs, the two sides, left and right, and I choose this. I call this forward bias, and then I can swap the buffs and put maybe it's a cold buff or some other buff here, and swap them, and I have reverse bias. How to characterize how good is a rectifier or a diode? We can use different numbers. One is the ratification, which is the ratio between the forward and the reverse bias. Or in other papers, this is also called ratifications, but okay, we chose to give it a different name to avoid confusions. We call it contrast, and basically it's the sum of the currents divided by the difference. And in the ideal regime of a perfect diode, the ratification goes to infinity because the reverse bias basically is zero current, and while the contrast will go to 1 because again, if you put 0 here for the reverse bias, you get J forward over J forward, you get 1. Okay, so these are the two quantities that we're going to use later to characterize the performance of the diode, so I hope it's very clear. Now, in classical systems, ratification was seen, I think, first in 2002, a paper by Dario and Casati, and there the idea was first you have to break the inversion symmetry in some way, and then you use nonlinearities. And the mechanism was understood there and then discussed and studied further. There have been a number of other interesting works, and there is a review here by various authors, including Hangi and Liebauer, 2012. And there, the idea that try to explains how what happens here is that you look at the power spectrum, and in the two halves of the chain, and you see that the response is very different whether you are at high temperature or low temperature. For example, here this describes this portion of the chain. At low temperature, the power spectrum, the response is only at these very high frequencies. When you increase the temperature, then the response can go also to lower frequencies. And then there is an overlap between the response on the two sides of the chain. And when there is overlap, you have good transport. And so this would be like forward bias, good transport, and here you have bad transport, okay? And that's how you get ratification. So of course, now you say, okay, let's do this in the quantum regime, and the natural step is to think of, instead of nonlinearities, we put strong interactions. Okay, so this was our plan. But before this, I would like to mention some works that I thought were quite useful for us to understand, and that they studied ratification before we did. And there was a nice work by Verlang and others in 2014, where they find an optimal rectifier. This only works with 2 spins, but the rectification is perfect. The same mechanism wouldn't work for larger systems. And there was also interesting works in 2014 by Landi and others, and there you use a magnetic field, different magnetic field throughout the XXZ chain they study, and they also see rectification. And even before, by Arakea and others, there was a work where, by using, they couple an XX chain and XY chain, and they use magnetic fields in the bath. And when you're in such a scenario, you can get the rectification. You see there is a different current whether you're in forward or reverse bias. So all these 3 setups, from my understanding, work well once you can use an external magnetic field that helps you to break the symmetry and make things happen. But we wanted to try, and there was also interesting works by Dar and Sigal and others, but I think these are a bit more connected to what we do. So what we wanted to look instead is a scenario in which you don't have an external magnetic field, but you only rely on the intrinsic property of the system, basically interactions which are within the system. So we started to look at a simple scenario, an XXZ chain. And you can think in general that the tunneling can be different in the various parts of the chain and also the interaction. But we simplify, and usually it's for rectification, it's usually convenient to have just 2 different segmentation the system in 2 parts. So we have a left part with some interaction and the right part with 0 interaction. And then we put the tunneling the same everywhere except at the junction, which we put it small to have a stronger signal. So you see, the left side is interacting, the right side is non-interacting, and then there is a junction. Then, how do we try to understand what's happening? We use a master equation in Lindblad form, and I will show later that this also does not rely actually on this modelization, but we use it to understand the problem. So that we have a density matrix, we look how it evolves in the system, we have the unitary evolution, and then we have the dissipative part, and the dissipator is described by these jump operators here. Just to give you an idea, so what the dissipator does is, suppose that we remove the tunneling here, what happens is that if we put the bath in this direction, on the left-hand side, I would try to generate an infinite temperature state. On the right-hand side, I will have a fully polarized chain pointing down. And if I invert the baths, then this side will be fully polarized down, and this side will be at infinite temperature. I will describe the stability of this on these choices later on. Okay, so this is the scenario. Now, what happens? What kind of currents do we get? Okay, so I will study the currents, the rectification, and the contrast, which I described before, but I remind you here what is the rectification and what is the contrast. Okay. For small system, we did exact diagonalization. Then when the system starts to become large, about 20 and so on, then we use matrix product states to simulate this. So now I look at the current in forward bias and reverse bias as a function of the interaction within the half of the chain. And I see that if the interaction increases, the current decreases, okay? But what is even more interesting is that the amount of current that we get in the forward bias is significantly larger than the amount of current that we get in the reverse bias. And this is already very large for systems of only just 8 or 10 spins. If you look at the rectification, the contrast, we see the rectification goes up very quickly as you increase the particle number from 4 to 10, goes from some unit, small number, to 10 to the 4, 10 to the 5, okay? And the contrast goes quite sharply from a small value to 1, okay? So when you saw this, we thought it was quite interesting, and we wanted to understand this better, okay? There is a very relatively sharp change okay, from 0 to 1. Okay, so what's going on? In order to characterize the system even a bit better, we also look at magnetization profiles. And this is for the forward bias. And we see that in forward bias, we see characteristic diffusive behavior. There's linear slope in the region where there is interactions, fairly flat in the region where there is no interaction. But if I look at the reverse bias and I increase the interaction increases in this direction. See, so the light blue curve is the one with the strongest interaction. We see that it looks a lot like an error function, which is a typical signature that you will see in the magnetization profile in the insulating regime. So then we look a little bit better. Is this really insulating in reverse bias once interaction becomes stronger? Is there a critical value of the interaction after which the system becomes insulating? And what is the mechanism behind this? Okay, so we look at how the current in reverse bias changes with the particle number. And we see that for small interactions, it changes but slowly. Instead, if for large interactions, like here I have 3 and 5, for example, the ratification is small and it also decreases exponentially with the system size. So a sign that the system is as the system size increases, becoming insulating. Okay, so what is the mechanism behind this? Okay, let's look at the system without the buffs, but we prepare in this situation where the reverse bias situation where all the spins here are down and here are in the infinite temperature state. And then and there is no coupling. Then I turn on the coupling. What's going to happen? At the interface, you're going to have a spin flip. Everything has to start with a spin flip. So you have to look at the excitation or the excitation spectrum of having such excitation into the system. And we see that it can be described by this type of matrix. And it turns out that if the interaction is large enough, then there is a gap to have this excitation in the system. And so when there is a gap, this excitation will be localized. If it's localized enough, we will not talk to the buffs, and so there will be no transport. Just to give you an idea, a clearer idea, we look at the smaller system, 10 spins, and we look at the excitation spectrum on the left and on the right, once we start from these configurations in reverse bias. And these blue lines is the excitation as we change excitation spectrum, we change the interaction. Of course, it will not change because there is no interaction on this side. While on the other side, you see the excitation spectrum goes down. And as you go, once you cross this point here, there will be no matching between energies. And so the excitation will be localized and the system will become insulating, basically. So if I look at the contrast, I see that all the places where there is an intersection between the two energies, then you have a low contrast. And then beyond this value of the interactions, then there will be the contrast will be very high. And we can compute for a thermodynamic system exactly where this value is, and we find this expression, JR plus square root of JR square plus JL square, which corresponds in our system to 1 plus square root of 2, which is where we are having this big change in the ratification in our system. And note this was a small system, only 10 spins, and the interface coupling was quite large, so that's why it's quite round. If we reduce this and we make the system large, that would be very sharp. Okay, so another way to look at this is to just, and also to show that it doesn't depend on the fact that we model this with Lindblad buffs, is that we prepare the system here in the infinite temperature state and here fully polarized or the other way around. And we look at the time that it takes for the spin, one spin at the interface to change by 1% its value. Okay, and we'll look at how the time that it takes to change 1 over time. It's here, and we see that this time scale explodes as delta increases, goes beyond the critical value 1 plus square root of 2. So as the system becomes large, and the interaction is large, it goes beyond 1 plus square root of 2, the time scale at which the spin flips a little bit explodes. Okay. So stability, we can try to change the buff parameters and see what the contrast would be in this scenario. So here I plot the contrast versus change a little bit the buff parameters. In this case, I change the region where there is infinite temperature. So in these regions will be not in infinite temperature anymore, but the contrast is still very large. Instead, if I change the other side, where I try to force the spin to be all pointing down, then the contrast is more sensitive, but you can still get a large ratification for certain values of the variation. So it's relatively stable, very stable in one direction for one buff, a bit stable in the other one. Then we can also check what happens if you change the interaction on both sides, okay, and see which scenarios you have a stronger contrast. And the stronger contrast, you get it when one is interacting and the other there's no interaction. These regions are the regions with strong interactions, and you see that if you put both to be the same or opposite, you get no contrast, which is because they have the same excitation spectrum. Okay, so we have shown that you can have very strong interactions, and due to these interesting many-body effects, we describe the mechanism and discuss the stability. What are we doing now? We want to use different types of interactions and see if we can get even better performance, especially when we have heat buffs. Okay, here there was being many buffs. We want to use heat buffs, and we're already in progress. So stay tuned, and then there should be hopefully new results soon. Okay. So the other topic that I wanted to show to you briefly today is about interplay of disorder, interaction, and dissipation. Okay, this is done with my group in Singapore. So when you put interaction and dissipation together, it's quite interesting because you can try to generate some peculiar states, and so this is known as dissipative state engineering. Okay, and also you can generate the out of equilibrium phase transition and so on. And a question is, what happens when you add disorder? Okay. On the other side, you know, the interaction and disorder are also extremely interesting to put together. You have interesting phenomena like many-body localization, mobility age, and so on. And the question is, what happens when you add dissipation? Okay. So we started to look at the interplay between these three factors: interactions, dissipation, and disorder. And in particular, we looked at the case in which we have engineered buffs, so which are buffs which are peculiar, that are designed to generate particular states. Okay, but since there have been no talk so far on many-body localization, I'll just give a little quick overview. The point is that in presence of disorder, even interacting system show localization, although it's a little bit different from endless localization. So there have been a lot of experiments in the last years, and one way people look at in cold atom experiments look at these setups is, for example, to prepare. You have an optical lattice. You put an atom every other side in the even ones, for example, and then you you allow the system to evolve, and you check what happens to the imbalance. In a non-interacting system, you see that the imbalance goes down quickly to zero, and in a strongly interacting system, you can have localization. This delta here, sorry, in a strong disorder system, okay, you can have localization. So this is disorder. Okay, now some signatures of localization, theoretically you can look, for example, entanglement entropy, and you see that instead of going to a constant value, will grow logarithmically until you reach finite size effects. Another important quantity that you can look at is the inverse participation ratio. What is it? You take the single particle reduced density matrix, you look at the natural orbitals, and then you see whether they are highly localized, and this you get the inverse participation ratio. And in this work by Baer and others, they show that for large disorder here, the inverse participation ratio is small, and it's independent on the system size. So what happens when you have a dissipation? So this has been studied in various ways. In some ways, they look at the system and they put another system next to each other, and they see whether the localized system can localize the other, or it's not localized anymore. That's one way. Or it's been studied with Limrad buffs, okay, or heat buffs, and see what happens. So this work here, for example, predicted that with dephasing you have the imbalance that we discussed just now. It will go down quickly in time, independent on the strength of the disorder and the strength of the interaction. Eventually, it will go down, and this is obvious. And this was also seen in experiments, okay, by Lushkin and others. So it's clear that dephasing destroys localization. But dephasing is just one type of dissipation, and you can look at other types of dissipation, and you can ask yourself whether it's still possible to see some signatures of localization in there. So we look at again an excitation, we put disorder. And then we have a dissipator, and the dissipator has jump operators of this form. This was studied first by Sebastian Dill and others, and also by many other people, including Saro. And here, what happens is that if two nearest neighbor spins are like out of phase, then they get in phase. If this was a BEC, if this was boson, not spins, this dissipator will generate a BEC. Okay. So this dissipator was realized experimentally in 2013 using a universal quantum computer with ion traps. And a similar system that what I'm going to describe now is also being studied by Vakulchik and others, Denisov and Ivanchenko and so on. And this is the reference. Okay. So what happens with this dissipation what does the dissipation do to the system without disorder? Suppose there is no disorder, what does dissipation do? It's easy to show that it would try to generate a system in which the magnetization is zero everywhere. And also, it's interesting to show that for the interaction equals to J, you generate a decay state, which is a pure state. So now what happens when we add disorder in it? Okay. As soon as you add disorder, you look at the magnetization, local magnetization. Instead of being a delta peak, you will start to have a certain variance. But this variance is very different depending on the strength of the interaction in your system. So disorder is able to disturb your system more and more. The way disorder can affect your system will depend on the strength of disorder. If you look at the variance, it will peak significantly around delta equals to 1, which is when you have your decay state. Okay, so the decay state is quite unstable to the presence of disorder. But now the general question is do we have signatures of localization? And again, we look at this inverse participation ratio. Okay, so we have the single particle reduced density matrix, look at the natural orbitals and their occupation, and we look at the inverse participation ratio, and we do the average over disorder, similarly to what was done by Beer and others. What do we see? Okay, so in this region here, it's the region for weak disorder. So the inverse participation ratio is small, so you have no signature of localization. But for large disorder, then we see that there is a non-monotonous effect of interactions. The inverse participation ratio goes down, and then it goes up again. And yes, and so here we could see we see some signature maybe of localization. Then we looked at these natural orbitals and we see what they look like. And in the regions where we have a strong disorder and strong or weak interactions, the natural orbitals typically are exponentially localized. So they're all exponentially localized. Instead, for weak disorder, we have always one natural orbital which is delocalized and has an important weight. So we do see some signatures of localization even in these steady states, which are per se, the steady state is throughout the system, but the natural orbitals can be all exponentially localized. So I conclude here. I've shown to you about spin diode and the role of interactions and how interactions can be used to generate very strong ratifications. And then we definitely want to look at now different types of spin chains and then the effects of thermal baths. And also we have looked at the disorder many-body systems and how dissipation can affect them and whether we can see some signature of localization in the steady state. And there is a lot of work to do there. This is just the beginning. There are many questions we still have to answer and many other things that we need to characterize. Also the effect of periodic driving, what happens in transients. So there is still a lot that we have to do in there. Anyway, these are the people in my group that helped a lot on these two works. And I thank them, and I thank you, and I thank the support. Thank you.